Preparing to live stream.
Вроде уже должно было.
Ну, вроде да. Да, пошло, по-моему.
Оно расстановлено там, да?
Паш, надо отключить это звуков. Что?
Да, их можно в настройках отключить, но сейчас это под списком участников должно быть меню с 3 точечками, и там должно быть, как-то он там называется.
Так, Игорь, ты меня видишь? Слышишь?
Сейчас, подожди. Я вижу. Да, привет, Саш. Сейчас мы только настраиваем трансляцию. Значит, Паш, что я должен сделать?
Там под списком участников должно быть меню с 3 точками, и там какое-то
самый раз.
Чего-то там чаем.
Я этим тоже не занимаюсь.
Нет, здесь нет. Mute participants on entry. Это что ли?
Нет, но это тоже можно включить, лишним не будет.
Нет, я просто, чтобы не взаимодействовал с YouTube. Давайте я вам передам хост и все.
Давайте, наверное, назад.
Я вас сделал хостом, Паш.
Сейчас.
А, нет, это я Сашу.
Ты меня сделал, наверное.
Да. Передай Паше. Значит, там вот справа participant, если сможешь.
Ну-ка, ну-ка.
Там есть participants.
Manage participants.
Да,
Так, Паша.
кликни.
Кликнул. Хомсписок. Да.
Около Паши нажми, там появится менюшка. More.
Make host.
Сделай его хостом, а то я тебя...
Yes. Паша, все.
Ага, спасибо.
Так.
Эти звонки надо отключить.
Ну вот вы все сделаете, Паша. Так, ну что, мы можем начинать или еще подождем? Нет, еще даже время не наступило. Так что...
По-русски будет?
Нет, нет, я вижу список участников не по-русски.
Ага.
Да. Сейчас, а где же? Винсент здесь, отлично. Так, share screen, Паша, мне попробовать сделать теперь. Мы вчера тренировались, но я, поскольку...
Давайте.
Так, сейчас, стоп, секунду. Сейчас, опять не то. Секунду. Вначале должен, как меня учили, должен наладить full-screen здесь. Так?
Саш, привет, ты не убирай только свое видео.
Пытается share сделать скрин.
Ну что, получается сделать экран или нет,
В
Саш?
состоянии. Так, подожди, а куда делся зум? А где же зум-то у меня?
Внизу маленькая иконка с камерой.
Нет, подожди.
В Англии, наверное, все надо отразить слева направо.
Ну, вот я сейчас отражаю, но не получается. Сейчас.
Саш, давайте я попробую помочь. Вчера у нас все работало. Это Антон.
Работало, я не могу. Я вот когда нажал это самое, почему-то я зум не вижу.
А он у вас включен, Zoom? Он должен быть включен. Если он выключен, вы его не увидите.
Я разговариваю,
ну вы разговариваете, да.
Да, поэтому почему-то я его...
Команд Tab, и вы должны увидеть эту синюю иконку. Синяя иконка с камерой, никуда она не денется, просто может где-то затеряться.
Почему экрана я ее не вижу? Сейчас еще раз. Нету. Что за чертовщина? Вчера была.
Если у вас очень много программ открыто, она может просто не помещаться на экран. Вы попробуйте стрелочкой покликать, и, может, вы до нее докликаете.
Сейчас попробую. Сейчас попробую. Quit, Skype. Так. Еще там что-то. Так, ну-ка, теперь. Почему же его нету?
Под Linux у меня этот зум иногда превращается в такое одно окошко маленькое с видео, которое надо потом разворачивать, и его довольно сложно найти в таком
Нет,
виде.
Паш, на Маке такого нету. Если вы, Саш, если вы с компьютера, то он должен быть.
Ну вот вчера же был он, а сегодня нет. Мне нужно... Сейчас, я закрываю тут какие-то...
Ну, можно сделать по-простому. Можно выключить Zoom и выключить Acrobat, потом включить Zoom и попробовать быстренько с самого начала через это все пройти и не искать, в чем проблема сейчас.
Сейчас, секунду. Что значит, еще раз? Сейчас, вот если я... Вот, может быть, так... Сейчас, share screen я не сделал пока, да?
Да. Вот.
Саш, ты сделал, поскольку тебя не видно.
Я сделал, но это, ты понимаешь, в чем дело? Так, а как же мне выйти в Zoom-то? Что-то я же в Zoom сейчас, правильно?
Сейчас, в Zoom, да. Саша, попробуйте просто выключить Zoom и Acrobat и запустить снова.
Выключить и Zoom Acrobat, да?
Да, и потом включить Zoom, потом включить Acrobat и попробуем еще раз с самого начала. Так может быстрее, чем пытаться разобраться.
И компьютер перезагрузить.
Этого я не говорил.
Сейчас все сделаем. Тогда попробую сейчас я. Так. Так. Так, сейчас. Так, вот сейчас как?
Прекрасно, сейчас видно вас.
Сейчас меня видно. Теперь хочу сделать share screen.
Давайте сейчас включим Acrobat.
Так, Acrobat. Включаю. Я его включил.
Включайте.
И full screen делаю, правильно?
Делайте full screen.
Так, теперь, значит, как вы меня учили, команд делаю.
Command Tab.
Вижу. Все, стоп. Секунду. Сейчас, секунду. Ну-ка, получилось?
А теперь в Zoom делайте share screen и выбираете вашу презентацию.
Так.
Все,
есть?
работает.
Супер. Ха-ха. Победа. Ясно. Окей. Игорь, should I start this?
Okay, it's my pleasure to give it speech to Sasha Veselov. He will talk about automorphic Lie algebras and modular forms. Okay, go ahead. And
Okay.
please mute all microphones, all but the speaker.
Thank you very much. Actually, Vincent, this is a joint work with Vincent Knibbeler, who is actually joining us also as well. So he will check if I'm saying something wrong. He will tell me. This is actually Vincent Knibler and Sarah Lombardo are probably the main experts in automorphic Lie algebras, which is actually, I would say, it's a term which is not maybe in full generality very well understood. And what I'm going to talk about actually appeared as what I thought to be something like simple exercise with the simplest possible example I'm going to talk about. But when we started to do this with Sarah and Vincent, it quickly became clear that it's not as simple, and actually more interesting, much more interesting, at least for me, than it used to be. So we discovered few important things which I would like to emphasize today, actually, in this area. So let me start now. Just a second. So let me start with, so this is the theory, of course, of infinite dimensional Lie algebras. So the simplest example is the loop algebra, which Laurent polynomial maps of C star into Lie algebra. Now, this Lie algebra, they play a very important role in the theory of Z-graded Lie algebra, as it was developed by Katz. Now, I'm not going to talk about extension of this. So think of just loop algebras, right? Loop algebras without extension. But what I'd like to talk about is twisting of this algebra, because if you have an automorphism of this algebra of, say, degree n, then you can consider twisted maps, twisted by satisfying this relation f of epsilon z equal to sigma of f of z. F of z is in Lie algebra, and sigma is automorphism of order n. Now, there is one result which I always took for granted, and it's very well known, and now I think that that maybe we well, it's certainly for me underestimated this Katz theorem. So Katz proved in 1968 that for every inner automorphism sigma, the corresponding twisted Lie algebra is isomorphic to untwisted one. So actually, it means that inner twist can be ignored, and we left only with automorphism of Lie algebra, which is in a simple Lie algebra case corresponding to the symmetry of Dynkin diagram. Right, that's why, you know, we have list of these affine Lie algebras, twisted. They labeled by the automorphism of Dynkin diagram. So for you have finite set of such version in each case, as many as symmetries of Dynkin diagram we have, right? So this, if you consider automorphism of Lie algebra, then they are for simple Lie algebra, they consist of large. The connected component of identity consists of inner automorphism, but there are other components labeled by symmetries of Dynkin diagram. The theorem say that you can ignore this inner automorphism, and therefore everybody nowadays starting with labeling them by symmetries of Dynkin diagram. But why? I mean, it's, of course, there is a theorem, there is a proof in the Katz's book, but somehow I didn't find it simple. I mean, it looks to me, it's a kind of, I would like to consider this as a deep fact, actually, which is non-trivial. And maybe the whole talk today is to explain why we should maybe view this Katz's result as less, maybe as deep one, actually, not just technical, but deep, right? Okay, so inner automorphism can be ignored. That's basically what Katz's message is. Now, so what are automorphic Lie algebras? So in the straightforward generalizations, these are, we can be viewed as natural generalizations. So C star you replace by Riemann matrix, and so by Riemann surface, and the cyclic group by discrete group G acting by automorphism on G and by biholomorphic automorphism of X, right? So now the study, I think the idea goes back to old paper of Sasha Mikhailov called reduction groups. And I think this was about around 1980s. So those who, so this is, I think, the time when Lax pair for Landau-Lifshitz equation was discovered by Borovik and Zhenya Sklyanin. And this is a kind of one of the most important integrable system in 1+1. It's Landau-Lifshitz equation, and Lax pair was depend on elliptic parameter, and it has certain transformation property. Lax matrix depend on elliptic parameter in a kind of automorphic way, right? And then Sasha Mikhailov had a paper where he said that one should consider what he called reduction group, but it came to this more general theory of automorphic Lie algebras later on. I think it's around the beginning of around 2004, where Mikhailov with Sara Lombarda, that time she was a PhD student of Sasha Mikhailov, they started to look at this more closely as a general theory. And they started with the most natural maybe example, punctured Riemann sphere, zero case, and this is, now this followed by further development of Sarah with Jan Sanders and Vincent Knibler, and which is now kind of studied this case in more systematic way. Now, it's interesting that the first non-loop example, the first interesting example, was introduced already by Anzager. Now, Anzager, it was realized actually only, well, relatively recently. I think the person it was Rohn in 1991. And let me say just what is Anzager Lie algebra. So in his paper, and this is a famous paper on 2D Ising model. So it appears as generated in relation. So you have AK and GK with the following commutating relation. Okay, so this algebra as it was shown by Rohn. I mean, it's so this is actually isomorphic. It's automorphic Lie algebra, where Z2 is acting on punctured on C star by involution, not by Z2 minus Z, how it is in Katz's case, but Z to Z minus 1. It's also asymmetry. And it turned out to be that if you use this symmetry, then you have different. You have algebra, which is oops. Okay. So now. Yes. So the first example, maybe the simplest example, and maybe most important example, when analog of Katz's result doesn't hold. I mean, it's in that case you cannot simply consider, you know, this is not the case. The analog of Katz's result here, they are not isomorphic. Left hand side and right hand side are not isomorphic. You cannot simply move this gamma into on the space of function. Okay, so this is now let's what we considered is what I thought would be a simple exercise, as I said initially. So if you consider now proper automorphic case, namely when X is upper half plane, hyperbolic upper half plane, and gamma group is SL2Z, acting naturally on upper half plane, and Lie algebra is the simplest possible. It's L2C. Okay, so in that case, of course, we have the theory of modular forms, which tells us that it's not enough to consider functions. One should consider also forms, modular forms, which are actually densities, if you want. It's f of z, dz to the power k. K is weight of this, right? And therefore, if you consider them as a forms, then you have this c tau plus d to the power k factor appearing, which comes from transformation of dz to the power k. And that's remember that a b c d is in SL2Z. The determinant is 1. Okay. So, so therefore, it's natural to consider not only invariant, but also invariant function, but also invariant forms. So this is very standard. That's nothing, of course, surprising if we consider this this function. And then, but now we have to specify so yeah, if weight is 0, then it's simply functions, and therefore weight 0 subalgebra is precise analog, straightforward analog of what was considered before.
Sorry, sorry, why from H2?
H2 is upper half plane.
Ah, okay, okay, thanks.
Yeah. I mean, we're using this. H2 is two-dimensional hyperbolic space, which is
thanks.
In this case. Right, but now we have to specify, because quotient of upper half plane by gamma is modular curve. It has cusp. We have to specify the behavior at the cusps. So usually it's meromorphic behavior. But this is important point, very important point, that analog of modular forms here, actually regular at infinity, will be we have to allow growing polynomial in tau. But remember that at cusp, we have cusp variable is actually q, which is exponential of 2 pi I tau. Exponential of q, and therefore when people saying that modular form is meromorphic at cusp, they mean variable q, not tau, right? Which is, and q is exponential. And this is this interplay between tau and q, which is exponential, is very, very important, because its q expansion is Fourier coefficient, and tau expansion would be something like Taylor coefficient, right? And the change from one to another is quite complicated and very important for number theory. I mean, this is going back to Ramanujan, and was one of the motivation for theory of modular forms, maybe in 20th century. Anyway, so what I want to say is that we have to consider, in order to come to in order to have the right object from our point of view, is if you allow slow growth. So if in variables q, it's log of modulo q, right, to the power n. So this is what we call log. But in tau, it's very easy. But remember that in tau, tau is wrong parameter at cusp. The correct parameter is usually considered as q, right? Q is parameter. Anyway, so this is kind of regularity. Regularity is actually it's slow growth. Log polynomial growth at infinity. So this is very important. That's subalgebra P. You can think of this as analog of regular modular form. But regular modular forms are simply regular at cusp. But here they are not regular. They grow, but they grow slowly. They grow polynomial in tau, log polynomial. This I'm emphasizing this because this is very, very important, because we define the object, right? I mean, this algebra, the answer will depend what kind of object you consider. So we consider holomorphic map satisfying this, and some restriction on growth at cusp, which is either meromorphic, like usual, or log polynomial, which is also usual, but in a different context. And let me now explain which is the context. But before that, let me simply formulate the result, and then we will see. So this is, we want to study this algebra, and for this we need to introduce classical Eisenstein series and Haupt module. I will tell about them later on in more detail, this classical, but those who are familiar, then we can say that E4 and E6, they generate the algebra of modular forms. So weight 4 and weight 6, they are generators. So they C of E4, E6 is algebra of modular forms. And it turned out to be that the answer is trivial. And then I remember I first was disappointed when we got to this after a long way. In a long way, we came to disappointing result, that it looks like theorem 1 tell us that, well, this is just theory of modular forms, right? Usual modular forms, because algebra P, we introduced, said something about log polynomial growth, but it's simply isomorphic to SL to C, tensor product to C. What, I mean, this is, this is something, what was the point? I mean, we have trivial algebra from which we can consider from the very beginning. The thing is that in isomorphism, And this is the same as in Katz. The fact that they are isomorphic, important thing how they are isomorphic, right? I mean, it's, and Katz actually explained in his book this isomorphism, but I think people usually not looking at this isomorphism because you need only answer. And if you need only answer, then you probably don't want to see this isomorphism. I want to show how non-trivial this isomorphism in this case, in order to make this point that maybe we should look at Katz's result as well. I mean, it's so suddenly I realized that maybe there is something interesting there. Anyway, so this is from the Lie algebra. It's just usual tensor product by usual modular forms. No growth, nothing like this. Okay, so this is one theorem, and as I said, I'd like to view this as a hyperbolic version of Katz's result. Now, second theorem is shows that if you consider meromorphic version, remember that M is meromorphic. You have poles at cusp, and M0 is when you consider instead of forms just functions, right? And these functions then with values in Lie algebra, which is SL2 C in our case. So it's you have E, H, and F as a standard generators of SL2, and the commutator is H and E are the same, H and F are the same, and only E and F is deformed. And it's deformed, you see, this is a function now of tau. And function of tau is just J minus 1728. Now, if you times H, if you puzzled by this 1728, this is the value of J function at the the modular curve. The fundamental domain is a triangle with cusp at infinity and two vertices, and the values of J at these vertices is 0 and 1728. So it reflects the fact that the quotient is actually not smooth; it's orbifold in a way, right? I mean, it's and this is kind of reflects geometry if you want, but it's not. It's so this is how it is. I mean, it now depends on tau, the simplest commutator. While in theorem 1, you can make change of variables, such that commutator will be exactly the same. HE equal to E minus 2F, and EF is H. So therefore, this is theorem 2 say that weight 0 it's not Katz's situation, it's a different one. Right, now, well, this is looks like not kind of natural maybe result to expect, but it took us quite long actually to get to this. And on the way, we learned about theory of vector valued modular forms. And this vector valued modular forms, they goes back to probably Shimura, the very 1959, and then Selberg also emphasized the importance of this. And for us, it was important the result which of Knopp and Mason and Frank and Mason, I mean, most recent, but so Knopp and Mason, I think Knopp was, he started this around 2000. He realized that there is something important there. Now,
sorry, Sasha.
yes.
Sasha, may I ask a question?
Yeah.
Is it true that at each point of the modular space of the modular curve, our Lie algebra M0 can be is isomorphic to the standard one?
I mean, it's you can view
not at
this
zeros of the right hand side.
Sorry.
Not at zeros, but at almost each point.
Yes.
Mhm. So
Yeah.
it's dependent on the point of the modular curve.
That's correct. I mean, except zero, right? J expect its orbifold points.
Yeah, except the orbifold point. Okay, thanks.
Mhm.
Sorry, I also have a question. Are there any explicit formulas for this H, E, and F as
Yes.
functions of tau?
This is exactly what I'm going to explain, because the interesting fact is that we can stop here, and if you're interested, but the most interesting thing is this isomorphisms, right? Because this I'm going to explain now how we give explicit formula for E, H, and F, okay? And they depend on tau in a very interesting and non-trivial way. That's the point. The point is not the fact that they are isomorphic, but how they are isomorphic. I think this is the most interesting, okay, bit, because otherwise that's it. I mean, that's the main result. So let me now, in order to explain, let me remind you the Eisenstein series. So Eisenstein series, well, I mean, that's, so what is modular form? Modular form is a function on a lattice. You have a lattice on the complex plane, and the modular form is a function of the lattice, where you better not to choose basis. You want to have bare lattice, right? And the simplest function is of course sum of 1 over element square, for example, but unfortunately it's divergent. So E2 will be divergent. But E4 would be okay already, and E6 would be okay. And they generate, E4 and E6 will generate the whole set of modular forms. One will be its scaling coefficient. Scaling is weight 4 and weight 8. That's it. I mean, that's the end of story. So we have a very natural function of the lattice. You can see the sum of elements of the lattice to the power k minus k. And if it's convergent, and if it's not zero, take it as modular forms, and it's enough only to take E4 and E6. That's fine. Now, few things which I realized only when look carefully. Here, sum is written not over M and N, but over M and N coprime. Okay, this is important if we want to consider arithmetic. The difference between this sum and another sum, when we compute the sum over all elements of, not primitive. So here over primitive elements of lattice. If you consider sum over all, the difference will be zeta function of k, which is of course known for even powers, and this is this will give, but it will give us some powers of pi and Bernoulli numbers, and pi will spoil, of course, it's not arithmetic. Now if you sum over coprime m and n, right? So this is ek, and sometimes another sum called gk. Actually, the best piece, I had to read all this modular stuff. It was mostly new for me. I had only very general knowledge of this. And the best piece about this explanation of this spot was Don Zagier. Don Zagier carefully explained that. He said that basically, so you have two sums, one over primitive elements of lattice, another one over all, and the difference is zeta function, right? But he said that both sums are important, because when you sum over this, you will have gk, and this is g2, g3 in Weierstrass form, elliptic curve, right? All this is related, of course, to elliptic curve. So if you sum, and if you want to do, so if you want to do elliptic function theory, you have to use gk. And if you want to do arithmetic, then you have to use ek. And the difference is zeta, but zeta is important function. So normalization, right? So this is a little thing. Just normalization if you want constant, but this is it. And then this is why Ramanujan was interested in this. It's generating function. If you consider this now, this is modular form, so it's invariant under shift, and therefore it is periodic function in particular, right? And periodic function can be expanded as a Fourier series, and this is Fourier series. So you expand it as Fourier series, and if you expand it as Fourier series, then you have remarkable arithmetic function, and namely sums of m's powers of all the divisors of n, and that's what Ramanujan was interested in, and this is actually remarkable paper where it's remarkable for several reasons. One is the fact which it's called usually Serre derivatives, right? But I couldn't find in Serre anything about this. The thing is that if you consider, that's fact number 2, if you consider ek at 2, for k equal to 2, then this series, which is written above, is convergent.
Я сейчас тебе вытру попу, Наташа, и вынешь свои пипи.
Hello? Hello?
For k equals to 2, you said that it's divergent rather than convergent.
Yeah, no, it's convergence now. In this form, it's convergent.
I see.
As a Fourier series, it's convergent. But in the top form, it's divergent, of course.
Okay, thank you.
So it's a kind of, therefore it's a kind of not. So the thing that this E2 is not modular form, right? Because you have to. It's not absolute convergent. It's convergent only after some change of variables, and this is this E2 of tau. Therefore, it's not. It's called quasi-modular form. In fact, this is just a connection. Now, this is, I thought that it's because it's called Serre derivative, I thought that it must be explained in this course of arithmetic by Serre, but I checked, there is nothing there. And it's a kind of mystery to me, but you know, people say that, well, it's essentially Ramanujan. Well, Ramanujan was not interested in geometry. So anyway, there is a canonical connection. And E2, which is this quasi-modular form, is just canonical connection. Now, this is essentially Ramanujan. So in 1916, where he started to study this, he also wrote, this is the following question. You have G2, G3. And they both G2, let's talk about Weierstrass, for example, form. You have G2, G3 in Weierstrass form. How they depend on tau? And this is not a good question because so this G2, G3 is E4 and E6. It turned out that you have to introduce G1, which is Weierstrass killing, this normalization, and G1 is essentially this E2. Now, if you introduce G1, G2, G3, or E2, E4, E6, then you have a closed system of differential equation. This is beautiful system. It's quadratic in the right-hand side, ODEs 3 by 3, and it contains all the theory. It's a kind of concentrate all the, from differential equation point of view, we're talking about solution of this system for 3 variables, E2, E3, E4. Now there is something here which I don't understand. Maybe some of you will tell.
Sasha,
yes.
How these relations are derived? Just checking, or there is something?
I don't remember, to be honest. I don't remember how Ramanujan. I had looked at this long ago. But let me tell you how we can derive, for example, the first relation. So the first relation, if we apply D1 to E2, and if we know that it's modular form, it has to be proportional to E4. You see? The same, if I know in advance that I'm doing the right thing, I know that the right-hand side is modular form, then weight 6, there is only one, I mean, by the general theory. Therefore, it must be proportional to E6. And when I take, when I differentiate E6, D6, of course, then I have weight 8, and there is only one 8. It's A4 to the 1. I only have to compute coefficient. That's it.
Why not E2, E6?
Yeah.
Sorry?
There's another E2, E6. The product also has weight 8.
Ah, yes. Right.
I mean, it's basically a two-dimensional space.
Yes. Sorry.
No, but E2, E6 is not modular.
Huh?
E2, E6 is not modular because E2 is not modular.
Oh, yeah. Sorry. E2 is quasi-modular.
Yeah. E2 appears only in the definition of the derivative.
No, this is normal derivative.
E2 is quasi-modular. It's not.
No, it's a derivative with an index. D6, for example, D6 contains E2 inside, right?
It's black. It's only black.
We're looking at the black at the bottom. At the bottom. No, but I mean, indeed, no, degree weight 8 is only 1, E4 squared. Because it's generated by E4 and E6. Right. No. So the first one is, when is it? It's when you have, weight 12, which is the famous delta discriminant. Then you have E2 cube, E4 cube, and E6 square. And the combination is discriminant of this cubic. Anyway, so if we would just know that this is indeed connection, right? Then we would derive it. It's up to coefficient. The bottom line is obvious, right? Now there is one thing which I don't understand, and maybe you can explain to me. So look at this bottom line. We differentiate connection with respect to the same connection. It looks like the right thing is to consider this as weight 1. Why is this? Here it's not the way it was derived, right? Ramanujan derived this equation, and this interpretation is much later, and I don't know who did this. And this clever person probably can also explain why is D1 should be written in the first, right? It's not weight 1. You think that it should be written D2, but it's D1.
Sorry, but why is it D1?
Well, just because of Ramanujan. Look at that. Look at the blue formula upstairs.
Yes, but it should be...
K is weight. It should be
yeah,
K.
indeed. And E2 is of weight 2.
2 is weight 2. Well, I mean, it's
So therefore-
quasi-modular, but it looks like
it's quasi-modular, but it's E2. It's quasi-modular of weight 2. So therefore, we are only allowed to apply dk to the modular form or quasi-modular form of weight k. So therefore, we should apply d2 to E2.
Yes, and we have nothing then. We have a problem then.
No, it follows from the blue line that we have exactly a minus E4 over 12.
Yeah, k
Which
equal to
basically
2. You want to take k equal to 2, right?
Yeah, and
Then it's d
d1
minus 1, 6.
and d1 of E2, I think it's basically not defined by the definition.
No,
It
d1
looks-
we define it by the definition.
Yeah,
This is on
And here-
modular form.
and here k is the weight of the form we apply dk to.
Correct.
So therefore, we are not allowed to apply d1 to
We are
E2.
not allowed to, but nevertheless, we formally can write down Ramanujan as d1 if we do. It
But
looks like
then what is
we are
the
not
reason?
allowed, but this is what actually happened, and I don't know good answer to this. Maybe I'm missing something simple.
So
but
that
it's
might
d1.
that might be a misprint basically, because it should be d2.
Well, I don't think so. I think we checked this, and I don't. It's a mystery to me. I mean,
Well, it's a well-known result that the algebra generated by E2, E4, and E6 is an algebra with differentiation, and that's exactly the differentiation given by this decay.
absolutely,
So
absolutely.
therefore,
Yeah,
somehow, well,
yes, and that's essentially what you said is essentially Ramanujan, because if you know Ramanujan formula, then it's done. Job is done, right?
yeah, well, because the
Polynomial algebra.
blue line can be proved basically from the definition of EK by the direct differentiation.
Correct. That's
somehow
what I think
straightforward.
Ramanujan probably did. But look at the interpretation which is on the bottom. I understand the second and the third, but I don't. I'm puzzled with the first one.
Well,
Because you're absolutely right. Why D1? It should be D2. But if you write D2, you don't have Ramanujan. And also, what's the point to differentiate quasi-modular form? I don't know. Well, there is some.
Maybe these two problems cancel each other. Because E2 is quasi-modular, you apply D1.
Yeah, but this is, I don't understand why. I mean, this is simply fact, right? I mean, what is written at the bottom is fact, but
but it's not defined.
No, D1 is by definition is what is written here, right?
Yeah, but if
by
you
definition, I mean, let's define decay like defined upstairs. Then I can rewrite Ramanujan in this way. What's the meaning of the first lie or the first formula? The other one is simply covariant derivative with respect to Ramanujan connection. Maybe we should call it.
I think this black for D1 E2 doesn't follow from the yellow or from the blue DE2 because it brings E2 squared and E2. Well, I don't know.
Yeah, but it's applied to E2.
Maybe I'm mistaken.
No, we apply to E2. So E2 times E2, E2 squared. Well, anyway, I mean, it's maybe it's something which is a kind of mystery to me. But anyway, so this is called people in modular form call this decay Serre derivative. I couldn't find the reference to Serre. If it's that general, maybe Serre just commented somewhere that this Ramanujan formula can be interpreted as derivative as connection, but this is anyway. So this is, you agree? I agree that this is a very well-known formula, and therefore if you want to consider differential algebra close under differentiation, you better consider E2, E4, E6. And therefore, if you just consider E4, E6, then you don't have good formulas. So that's why for G2, G3, we don't have good differential equation in tau, right? But for E2, E4, E6, we do have, and this is great Ramanujan, okay? So So this is, we need this because this will play with this. E2 will appear. Now, second surprise is that, you know, so the simplest non-trivial form, therefore, modular form is a tricky one, E4. E4 is the first nonlinear, and it depends on the transcendental function. Look at this. We have something of weight -2, which we called A -2 of tau. I claim that this is a modular form of weight 2, which is, remember that it's in our space because we allow to grow polynomially in tau. It's not Q, it's tau. It's log Q. Let's check this. Let's do this calculation. This is very important. And probably the first, I try to find who is the first to observe this remarkable fact. And it's known in vector valued form. And it looks like Shimura, 1959, I guess. Anyway, look at this. We had different interpretation of this formula, but somehow let's look at this. So so I claim that this is weight -2. There is no such thing in classical modular forms, right? But in automorphic, in this Lie algebra, we have -2. If we shift. Then we have this, right? Tau to tau plus 1. I claim that this is the same as triangular conjugation by triangular, easy calculation, right? This is fine. And then n -2, if you replace tau to 1 over tau, right? Then it's again a very easy calculation, show that it's tau -2 of what you expect to get. Again, easy calculation. So that's a prize. In the classical theory, it was E4, the simplest non-trivial modular form. Weight 4. Here we have weight -2. And this is genuine because we allowed polynomial growth in tau. It's valid, it's fine. It's considered as slow growing at cusp. And by definition, so it's eligible element of our Lie algebra, and this is modular form of weight -2. Nothing like this exists in the classical theory, right? This is now, of course, as I said, we mentioned here Knopp and Mason, but it's already because they develop general theory basically. They this log polynomial essentially it's their idea, but it was already in Shimura in 1959. He has a vector valued modular form. So if you consider, so we consider G valued, where G is Lie algebra. But if you consider just the first column, tau 1, then this is what Shimura considered and Knopp and Mason considered. So then it would be vector valued modular form with the same, exactly the same definition. So the only, if we ignore the structure of Lie algebra, then this vector valued modular form is a big subject starting from Shimura and then Selberg and then well, I mean, it's so, but for us, it was Knopp and Mason, okay? And this is, but somehow we discovered this ourselves from different perspective. And anyway, so this is a kind of surprise. There is polynomial modular form, not transcendental, but just simple, very simple polynomial form. Okay, now if we have this modular form, then we can apply now, we can differentiate them using connection. We have connection now, and we can apply this, right? And then we have two more forms, 0 and 2, -2, 0 and 2, and this is of course you will of course guess this will be a basis of SL2, right? Weight -2, 2 and 0, right? But look at that. I mean, this is we're going of course in this direction now. So Knopp and Mason actually showed that in some even wider, it's a kind of Cohen-Macaulay property that, of course, they did not consider Lie algebras, right? They consider vector spaces. So, this vector valued modular form, they prove that they are free module over usual modular forms, because you can always multiply by usual modular forms, and then you have, so vector valued modular forms are module over usual modular forms. And they computed Hilbert series, and Hilbert series is this. Therefore, we can show that they are actually form a basis, therefore A-2, A0, and A2. However, it's not the end. I mean, we should do something else, because if we act by, we want to consider A0 of tau as H, as mu H, right? And it won't work because commutator will give you extra tone, which is E4 divided by 16. However, it's not a big deal. You have to slightly correct the definition, right? So first of all, you have to introduce this 2 pi I factor. And second, you have to do this little change. So this is E, F, and H, right? So this is how it looks like. Okay. So this is change of basis, which Pasha asked. What is this? So F is just our tau polynomial form, but H and E are quasi-modular. Well, I mean, it's expressed through quasi-modular. It's a proper modular forms. As a vector valued modular form or G valued modular form, they are proper modular forms, right? So E2 is now appear as proper modular forms, but only as a part of, well, part of modular forms. So this is a combination of tau and E tau, E2 of tau. Both are illegal, right? Neither tau nor E2 of tau were illegal in the usual modular world. Now here it's exactly what you need in order to do this isomorphism. Claim this F, H, and E, F, and H satisfy standard SL2 C relation, and this is that's isomorphism of the graded even Lie algebras, right? You can denote, well, E4 and E6 by abstract X4, X6, and therefore it will be this. Okay, so this is here we used, of course, Knopp and Mason result, because we using them we can prove that they generate indeed the whole algebra. This generate the whole algebra.
Sorry, maybe I missed, but you have on the next slide this J times
yes.
J minus.
So this is the next thing. That's second isomorphism, and in that case we have the same EF and H, the same, but now we have, we put extra factors. And delta, is it written what is delta? Did I say what is delta? What is delta? Just a second. Delta is discriminant. So what is this? Let me remember. Maybe in this something like
E4 cube minus E6 squared, right?
Yes, I think it's without coefficient, is like you said.
What you had in denominator in this formula of the commutator, E bar with F bar.
Sorry, say it again. Yes.
You have, if you consider your formula of commutator with this E bar and F bar, yes, you have something dependent on J in the right hand side, and it has denominator.
That's correct.
And it can come only from, and denominator is just this E4 cube minus E6 square, and it can come only from these deltas.
That's correct. That's correct. That's correct. Yes, so what's interesting here is that and actually Vincent and Sarah, they have this phenomena discovered in this Riemann sphere case. Often there is an analog of Cartan subalgebra. You see, H behaves as H bar, behaves like proper Cartan subalgebra. It's acting on E and F exactly as it's supposed to act, and it's only the remaining commutation relation are changed. Yeah, so let me say a few words what we're doing now. We actually updating now, we soon put new version on the archive. But what we can generalize, so SL2Z, we can generalize, we can change to any finite index subgroup. I mean, the theorem 1, I'm talking about theorem 1 at the moment. Any simple Lie algebra, SL2C, we can replace by any simple Lie algebra. But the action of gamma, gamma of course is naturally acting on the upper half plane, but action on, remember that gamma should be, there should be representation in automorphism of Lie algebra, and it comes from embedding of SL2C into the group, into the such representation. What is it, Jacobson-Morozov, that you can label them by nilpotent elements of Lie algebra. So this representation. So we have this SL2 triples, which were discussed by Dinkin, I guess. No, Dinkin, yeah, I mean, the big story about SL2C subalgebras. So anyway, any of these representation which are inner in a way, for them always we have always analog of Katz result. They are replacing inner analog of inner representation. But there are different, of course, representation. SL2Z is you don't have to induce it from SL2C. these actions. And some of these representation were known as while representation, and they are related to Jacobi modular forms. Again, this is another big subject which we didn't look into this so far, but there are some. It probably cuts like result isomorphism is not true anymore. But what we have instead, it's not. It's a very interesting question. It's untouched for us at the moment by us. Yeah, so SL2C, SL2Z is, if PSL2Z, for example, in principle, it's just, you know, it's just free product of Z2 and Z3. So it's easy to construct. It has plenty of representation. You simply take any involution, any order 3 elements, and they generate representation for PSL2Z, and the 4 representation of PSL2Z. So there are plenty of course, representation. It's a kind of wild problem, representation of SL2Z. So how much, what happens in this world, we don't know. And of course, this is not what I had in mind, this application of integrable system. Also, although, as I said, motivation for Mikhailov and Lombardo were related to Lax representation of integrable system, I don't think that in our case, I wouldn't expect interesting application simply because we have isomorphism. We can, as Lie algebra, it's isomorphic to just Lie algebra tensor product with usual modular forms. So it's not very interesting from this point of view. But I'd like to say that it's mainly because of Zhenya Ferapontov and work with Sasha Adesky. Modular forms now appear in classification of integrable system. At the moment, it's related to the dispersionless integrable system in dimension 3 and 4, I guess. So this is there is this new work by Don Zagir, actually joined now this program, which was initiated by Zhenya Ferapontov. And there are very interesting results there. But it's not related to automorphic Lie algebra. I should say that modular forms now, so in their work, they are much more relevant, and but this is different. It's not related. So maybe where it is related is it may be more what we did may be more relevant to conformal field theory, maybe number theory. But again, this is just speculation. I don't have concrete application in mind. And this is the reference to our paper, which we hope to update soon, actually, with this more general result. That's it.
Sasha,
yes.
Any questions?
Yeah, I have a question, if possible. Sasha, do you have any ideas how this could look like for Riemann surfaces of higher genera, of higher than 1?
Right. Well, the first thing, of course, you have to have this this fundamental group act on by automorphism of Lie algebras. And here, for example, we have this fact that SL2Z is embedded in SL2C, and SL2C can be embedded in any simple Lie group, we know how, and stuff like this. Now, if you have, for example, genus 2 surface, right, then you have this fundamental group, and we have to see, I mean, the first question, what class of representation? So automorphic Lie algebra is two things. First, you know, this group, which is acting, let's say, in our it's uniformization, right? First thing is uniformization. You want to have this group acting on upper half plane with compact, for example, factor. And then you have to have representation of this group in the automorphism of Lie algebras. And as we saw, I think it's very important to have this good understanding of this representation. What we did, we of course induce it from SL2C, and where we know everything, right? I mean, representation of SL2Z is wild problem, but the representation of SL2C is a standard, you know, undergraduate material. Now here, this automorphy, this fundamental group, to be honest, so where so where I can see maybe some progress is if we consider punctured torus, right? Then it's of course free group. But again, I mean, free pair of automorphism of Lie algebras. No, I don't know. I don't know. I mean, it's clear that what's good about this, we were able to reduce our problem to a manageable size, basically, right? And then prove general result. That's what we did. And this is, you know, finite index subgroup of gamma, any representation induced from SL2C. If we relieve this, if we go beyond, as I said, for example, while I don't know what will happen, I don't know even how to, well, I mean, this is, to be honest, what next? We would like to consider what happens if we consider arbitrary representation of SL2Z, or maybe val representation for the beginning. What happens there? So the key thing is that I don't know how to approach this question of what is a good class of representation of fundamental group of genus G surface in Lie algebra. That's a crucial question. Anyway, natural question, we didn't go that far yet.
Okay, thanks, I see.
Okay, if there are no more questions, then thanks, Sasha, again.
Okay, thank you.
Excuse me, are Ziegler modular form natural candidate for this situation?
Sorry, say it again.
Are Ziegler modular form natural candidate? Yes. SP to K instead of SL to Z.
Yeah, this multidimensional generalization, right?
Yes, yes.
Right. Yes, that's true. I mean, about multidimensional, we have thought a little bit because what Zhenya actually has done, I mentioned this, they consider that's exactly multidimensional, right? Multidimensional, yes, there are natural generalization, but this is generalization indeed, yes, SL, yes, it's multidimensional, yes, yeah, of course. They considered, I think, Picard modular forms in particular case, but Ziegel is, yes, yeah, agree.
Thank you.
May I also ask?
Yes.
I mean, you're speaking about the inner automorphisms. So, for example, we'll consider the ADE algebras.
Yes.
And we know that there are some outer automorphisms, and they result in some connection between the Drinfeld Sokolov hierarchies.
Yes, of course.
For example, the B and C Drinfeld Sokolov hierarchies can be obtained from A and D hierarchies exactly via these outer automorphisms. And the inner automorphisms, should they also generate some new hierarchies?
No, I think this is the point. I mean, according to Katz, there is no point to considering the automorphism. But as I said, I mean, I got used to this fact and I thought it's a kind of trivial, probably, you know, but now I'm of different opinion. I think it's important, deep result, but because I think.
So, but still you're stressing that the automorphism is really non-trivial.
Sorry, say it again.
You say that automorphism is non-trivial. So it is your result is that it is highly non-trivial.
Yes. The same in Katz. I think it's not maybe highly, but it's non-trivial in Katz already. I mean, that's what I found surprising when I look carefully at the proof. There are actually lemmas which I think to me looks like I think it's quite maybe case by case eventually. I don't know. Required. In Katz, I'm talking about Katz. So, but after Katz, we can ignore inner automorphisms. Automorphism. Because they don't affect, you're saying that maybe
they affect
maybe the
dispersionless limit.
The isomorphism is important. Well,
for example, in the dispersionless limit. So that could potentially result in something non-trivial.
This is maybe, that's why I said that maybe we should look at more closely to Katz's result. Maybe you, this is my point. Maybe this inner automorphism should not be completely ignored. Because yes, as an algebra, it is isomorphic, right, to the original one. But this isomorphism is non-trivial. Maybe it's important that this is not, because in our formula revealing that there is something going on, very non-trivial, right?
But even for the A case. So I would somehow expect that, well, I would love to see that there is nothing new for A and something special for D.
Because of why special for D?
Because there is a Dubrovin's conjecture about the classification of algebraic Frobenius manifolds.
Yes. How it is related, sorry?
So there was a conjecture of de Brovin that one can construct all algebraic Frobenius manifolds with not polynomial potentials, but algebraic, exactly via the choice of the quasi-Coxeter elements in the Coxeter group. So these are indexed by the different choices of the quasi-Coxeter element. And for A, there is just one. For D, there is plenty of them. I mean, in the number.
I see. I see. I see.
So, and his conjecture was even proved in one case or two cases, and that was exactly by some reduction of some hierarchies.
When was it proved?
He had a student, Dina Yasser.
Yes, yes, it's one of the latest paper, right?
Yeah, I think he only has papers about this.
I see. I should look at this. I actually I didn't look at. No, I don't. I have no intuition. I mean, but to me, the whole thing is indeed worthy to look again. I mean, why? Maybe these inner automorphisms are important too.
Okay, thanks.
Thanks, Sasha.
Okay. Thanks.
Спасибо, Саш.
Счастливо, Андрей.